Hi, good morning, good evening, whatever time zone you're on. So what I'm going to be looking at here. I'm going to try and just fit in, well, essentially everything I covered in class. So we are going to be looking at a topic called calculus, and it's going to involve two topics. One of differentiation, and this is the one I'm going to be covering here, and the other one later on about integration. So calculus, it's a massive topic. So initially we're only looking at differentiation. Then we will move on to integration, but not in this little segment here. Like I'm saying, it is massive. You can consider it to being like an apple. We like stories. These are analogies. So consider this to be the calculus apple. It's vast. And there's other stuff out with that in the fruit and veg stall of mathematics land. So for us, see, for the people involved in calculus who pioneered it, they didn't hold that in their hand entirely, put it in their pocket or their lunchbox. For them, they were lucky if they could get a sizable bite out of it. No, a sizable bite. They were the people who pioneered it. Later on, 100, 200 years later, a lot of very clever people came along as well. So maybe these were my professors at university. And see, for them, they didn't get a bite out of this apple. No, most of them weren't capable. So what they got a little lick of that apple. Okay. For health and safety reasons, the tongue does not touch the apple here. Okay. For someone like me, or one of your other lectures, we don't even get a lick. We're unlucky. We're unlucky. Oh, if we just get to stroke it, or nearly stroke it. Not quite. Okay. That's fine. I think you can see where we're going here. And maybe people at university, good students who do a lot of mathematics, they don't even get to touch it or attempt to touch it. They get to look at it at a distance. Okay. And that's the students who actually study quite a lot of it, 3, 4, 5 years. They get to look at it from that distance. And in certain other courses where they don't do maybe a lot of maths, maybe they only do 2 years, they get to look at it a little bit further away. And also, maybe if you look at it solidly for even an entire year, where I'm just talking about calculus, not other topics, you're looking at it even further away. See for yourselves. I think this is where you are. Just about there. Okay. Can you still see it? Right. So realistically, that is where you are at. But actually, that is good for you. You don't want to be there, 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 there. You don't want to be there. You just want to be having a little peep at it. So that's what we're actually going to go and do. Now, we're going to go and have a little peep at our version of calculus. Okay, right, so we've got it all set up here, and if you're in class, then that's fine. So what we're going to do is, the differentiation is all about recipes, and the recipes means we've got a formula sheet, so we'll be referring to formulas. Here, these are the mathematical functions we're going to look at on the left-hand side. The things called the derivatives that will get explained along the way are on the right-hand side. We're just moving numbers about the page. So that's what we're going to do. So let's just dive in there, and we're going to speak about basic differentiation. And so for us here, what it's saying here, okay, I know you can read. So differentiation, it does look at how one variable, we tend to look at x as one variable. You can think of that as being a little letter. So how does it look with x compared to another variable, say y? Okay, so that's what we're looking at, how x compares to y. And this is usually two variables we use, and we use them in conjunction when we're graphing things with an x-axis and a y-axis. Because sometimes graphs help us analyse things a little bit better. So let's move on swiftly. So what we're doing here with differentiation, we're really looking at the steepness or the gradient of specific points on the curve, right? So we'll have a mathematical function. You can call it an equation if you want. It's really a function. A function is a processor. It processes x, you get y, or whatever the variables are. So we've got some function, and maybe we can graph it. So what we're looking at is any specific point. We want to know the steepness of that point. So the steepness of there, we can get that from actually putting a line on it, a tangent line. And the steepness of the tangent line is exactly the same as the steepness on the curve. That's what we're doing here. So that's the steepness at that point. But if we move along somewhere and we put a tangent line, the steepness seems to be a little bit different there from that one. So as we move further along the curve, just picking arbitrary points, the tangent line gradient is exactly equal to the steepness on the curve. But it changes all along the curve. Sometimes they'll have equal gradients along the curve. Right, okay. We've dealt with gradients before, and gradients are just a change in basically the height over the change in the length. So change, you might have seen that before. We like to shorten that to delta. We Greek capital letter delta triangle. So the change in y over the change in x. That's what we've got there. But for reasons we won't get into in any detail, we don't like this capital letter delta, so we'll use just maybe a common D. Is it Arabic? I don't know. So instead of delta y over delta x, we will have dy over dx. That's what we're going to have there. Right. So that's our gradient function or our derivative function. So before I go on to that, let's see. We'll just continue that. So dy by dx. So I showed you earlier, we're just going to go through certain types of function. Given the original function, we'll find the derivative. That's what we're doing here. So this one, a number times x to a power, something. So let's just get the rule. So according to this, if we want to differentiate dy by by dx. This here is just what happens here. We're going to attack the power, take the n value, that's the power, bring it down the front, and we'll multiply anything in front of x. That happens to be a. Don't touch x, but subtract 1 from the power, because that's the rule. Somebody's made this up for you, and I've given it to you. That's the rule. Okay, and it's on your formula sheet. Right, let's go for a little example. A x to the n, bring the power down the front, it'll multiply the 7. Don't touch x and subtract 1 for the power. Next part is tidying up. 5 times 7 is 35. 5 take 1 is 4. That's you. What you've found there is a derivative, which is commonly known as a gradient function. Later on, we'll be doing stuff with this. Initially, you are just moving things and tidying up. Okay. Square root of x is a very common mathematical function, but we need x to a power. So you might know square root of x is x to the power of a half. Okay, but we've only got 1 in front of the x, so that is like ax to the n. Let's apply the rule. So according to the rule, bring the half down the front when we're differentiating. Bring the half down the front and subtract 1 from the original power. So it's a half times x to the half minus 1. Let's tidy that up. So it's a half times x to the negative half. That answer's fine to there. You can leave it like that. You have found the gradient function or derivative. However, sometimes I don't like having negative powers, so what they might do is take the x with the power downstairs next to the 2, and it will change sign, and then they might exchange the x to the half to its old-fashioned notation of the square root of x. If you were to look at a textbook, your answer would probably look like that. So we need to be able to go between half x to negative half to 1 over 2 root x. That's just laws of indices. Okay. Right. This is just talking about notation here. So sometimes we use the change in y or the change in x, or sometimes if we start with y, we just might use a dash notation or y dash. Other times we use the function notation f of x, that's with f stuck to the bracket with x in it. So that just means to get an answer for y, we need to put an x into the function f. So here we incorporate the dash notation here. So when I find the derivative, instead of f of x, that's the f stuck to the x in the bracket, I just use a dash, okay, and the original rule stays the same. Right, so this is just the notation we're looking at here, and I'll be chopping and changing with them. Okay, and I don't want that. I don't want to restart. Okay. Right. 5:30 in the morning, we don't want a restart. Right, okay. This here kind of looks the same, but actually it's a different function. We've got it here and we've got a different rule. So different function, different rule. So according to this, when we go and get the derivative, changing y over changing x, bring the power down the front. But there's an additional thing that happens here. The number in front of x, sometimes called the coefficient, comes out the front, multiplies your n value. Next thing you do is bring down the bracket with the contents. Don't touch them and subtract 1 from the power. That is it. Okay, let's have an example of this. Looks the same. So according to the rule, you've got in your formula sheet. So I'm using the y dash notation here. That's still a derivative. Bring the power down the front. Bring out the number in front of x, the coefficient of x, and later on we'll see why that number's coming out, because it's 7x, so we'll know why. So times it with 7. Bring down the bracket with its contents, don't touch it, and subtract 1 from the power. Next thing in here, let's tidy up. Let's do 4 times 7. Bring down the bracket and subtract 1 from the 4. That is us done. Okay. With these videos, you can always pause it. Okay, so that's why I'm trying to go through this swiftly, because I'm trying to fit in 3 kind of mini lessons in here. Let's move on. Okay, that kind of looks the same. 3x minus 1 to the 6, that looks like something we had before, but the thing is, it's in the bottom of a fraction. We're not allowed to have it there for whatever reason, so we need to bring that bracket upstairs next to any number that's there, but using laws of indices, we change the sign of the power. Okay, so that now looks like the thing that we want, and the thing that we want, that's ax plus b to a power. That's what we want. The 4 just, it comes along for the ride. Okay, so here we go. Bring the power down the front, y dash. So the 4's coming along for the ride. So now bring the power down the front, put it in a bracket, keep it safe. Next thing, go in and get the coefficient of x. Bring it out. Okay, that's the numerical part done at the front of the bracket. Bring the bracket down and subtract 1 from the original power. Right, let's tidy up. 4 times negative 6 times 3 is negative 72, I believe. Bring the bracket down. Negative 6 take away 1 is negative 7. That's us done. Okay, there's no need to take the bracket downstairs and make it a fraction and make the power positive 7, but you could do if you're feeling good. Done. Okay, next rule. Here we're going into trigonometry. According to the rule here, to differentiate this, follow the rule. The rule is on your sheet. We got a sign, and this is what happens to it. Don't make stuff up, that's my job. According to this here, either y dash or dy with dx. What happens here, we go inside the bracket, bring out the coefficient of x, the number in front of x, which is a, bring it out, sine goes to cosine for some unknown reason to you, and then bring down the bracket and its contents. That's you done. Let's go for its partner, cosine. Here, dy with dx, y dash, going for dy with dx. This time, for some unknown reason, because it's cosine, it goes to negative a. Cos goes to sine, and then bring down the contents of the bracket without touching them. That's it done. Okay, this is just a build up. We just want to go through the little recipes here. We're just moving things. Let's go for an example here of a sine or a cosine. We've got a cosine. It looks like ax plus b can be plus or minus a number. Okay, so according to the rule, I'm using y dash. It goes to negative. I put that in right away. Cos goes to sine, but before that, the number in front of x in the bracket, the coefficient of x, it comes out the front. Okay, cos goes to sine, and finally bring down the bracket with its contents, and that's you done. You're just moving stuff about. Later on, we'll be putting values for x. Okay. Right, but sometimes we have what are called special cases. Differentiate y equals 3. I can't see any x's here. I could put them in here, because that'd be 3 times 1, 3x to the 0. I could put that in, but I just want to show you here, what does the graph of y equals 3 look like? Well, hopefully you know y equals a number in terms of Cartesian coordinates, x and y that I've got here. It's just a horizontal line where the height is equal to 3 everywhere. And what's the gradient of a horizontal line, whether it's 3 or not? The gradient is 0, so I'm using m to represent the gradient 0. Differentiating is all about finding the gradient function, or the gradient. Well, the gradient here, the gradient function is 0. So any constant number on its own, when you differentiate it, the answer is 0. That's a special case. Please remember it. Okay, here we've got a little pick and mix. We've got an ax to the n, we've got a sine of ax plus b, and we've got a number on its own. Let's go through and differentiate them one at a time. So what you're doing is you're having a look at your formula sheet and you're trying to match them up. So one looks like that, one looks like that, and one looks like a number on its own. Okay, so let's marry them all up. So dy by dx y dash, whatever you want to put down, 5x cubed. The 3 comes down to multiply the 5, and we'll subtract 1 from the 3. Next one, sine ax plus b, the 2 comes out the front, sine goes to cosine, and the bracket comes down. The 7, it's a number on its own. Because there's other stuff there, its derivative is 0. We don't need to show that. That's done. Okay, so there's a little bit of tidying up here. The 3 times 5 is 15. The 3 take 1, and the power is 2. That's fine. And the secondary part, the trig part, that's sorted. That is our answer. So we're just moving things about the page and tidying up. That's all we're doing here. Let's move swiftly on. And so we'll get, this is a natural exponential. We've seen this before, hopefully. So let's just go straight to the rule. Here, natural exponential, so that the exponent, the power, is ax plus b. I hope you've noticed this appears quite a lot. So when we differentiate dy by dx or y dash, what happens here? We go and grab the number in front of x, and coefficient of x. It's actually a derivative of ax. It's just a comes out the front. Now what we do, because the rule tells us, once we've brought that down, we just stick the original function next to it, the e to the ax plus b. That's it, done. Okay. Then let's apply it to an example. So we get e to the 9x take away 7. That's e to the ax plus b, plus or minus. So when we differentiate it, y dash dy by dx, just bring the x number down the front and then multiply it by the original function. That is it. That is one of the easiest ones to deal with. Okay, let's move swiftly on. And there, what I did, I shouldn't have. What I'm going to just briefly pause. Let's see, can I pause it? Will that pause it? Okay, so let's now get another example, except we've now got a number in front of the e part. That's fine, so that's 6. That'll just come along for the ride. So when I differentiate dy by dx or y dash, that 6 just comes down, and it's the e to the 5x part I'm interested. So I go up to the 5x plus 1, I bring down the x number, which is 5, and then I just stick the original exponential part next to it, so that's e to the 5x plus 1. And finally, 6 times 5, I just tidy up. That's the answer. Okay, that's us all done. Okay, so that looks like we've done. Okay, this is the last one. So I'm just going to check my formula sheet. Yep, this is the last one I'm going to look at. Right, so once we've done this, I'm trying to get to the crux. But a lot of this is moving the numbers about. That's what it's all about. Right, okay. ln is natural logarithm. You should have seen that before. Right, so when I'm differentiating y dash dy by dx, what happens here is we go and get, again, the a value. We're going to create a fraction. That a goes on the top, put in the fraction bar, and downstairs we put the contents of the bracket. And that is you done. That is the derivative. Okay, let's go for a little example here. The natural log bracket 2x plus 5. So according to the rule, dy by dx or y dash. I'm using y dash to confuse you, or get used to it. Okay, So according to the rule, go and get the number in front of x, coefficient of x, actually the derivative of 2x. So here we go. So that's 2, and downstairs we'll just put the contents of the bracket, 2x plus 5. So some of you start thinking, okay, we can cancel out a 2. No, you can't, because 5 is not divisible nicely by 2. So just leave it like that there. Don't overthink things. That's your answer. Okay, let's get another one and see what happens. Here, we don't have a bracket. That's because the b value is 0. That's fine. So it's a natural log of 7x. But we've still got an a value, a number in front of x. So I'm going to differentiate dy by dx or y dash. Take the 7, put it on top of the fraction, and the 7x goes downstairs. But this time, we have multiples of 7 top and bottom. We get 7 times 1 in the top, 7 times x in the bottom. Divide the 7 out, top and bottom. 7 divided by 1 in the top is 1. 7x divided by 7 is just x. So that's why we are left with 1 over x. If my computer plays ball. There we go. So that's it. So that's just a wee bit of practice, and you'll have quite a lot of practice in your exercises. Alright, let's see. I think we're going to have a wee combination here. So I've given you two. So one's natural logarithms, one's a natural exponential. So like I keep saying, you can just freeze this, have a look at your formula sheet and say, well, have I got ones that match up with these? I do then. I know where to move them to. So here, when we differentiate dy by dx or y dash, the natural logarithm, it's going to go to the x number 3 all over the contents of the bracket. Okay, everything is not divisible by 3, leave it. Next one, e to the 3x, so that's like an ax plus b. We don't have a b value, well, it's really 0, but the thing is, we've got a number in front of x. So what happens here, it comes down the front, and we just multiply that by the original exponential function e to the 3x. No tidying up to do here, folks. That's it. Done. So, I spoke earlier about y equals 3 I had. It was a horizontal line. Horizontal lines are y equals a number, a constant. Its derivative is all 0. But there's another one, but it doesn't seem to fit the rule. But it actually does. So if you got y equals a number times x, or whatever the variable is, it could be t, could be whatever, r. Here, that should be really 2x to the 1. So I don't want to go through the routine of why we get the answer. I just want to show you what does the graph of y equals 2x look like. Well, hopefully you know that y equals 2x is a line. It passes through the origin where x and y meet. Y equals 2x. It's a straight line. It matches up with mx plus c. The c value is 0, so we don't have it there. But what we do have, whatever's in front of x is actually the gradient. We know the gradient is 2. This is what differentiation is all about. It's about finding the gradient function. That m and the 2 match up. So our derivative, or gradient function, is actually 2. So any number times x, or whatever it is, when it's a power 1, just get rid of x and just have 2. That's it. Like I said, another special case. That is us done, folks. Right. Okay. I'm going to leave that there. So I've sort of went through 2 little mini lectures here. Let me see my time. Let me see my time. Okay. It's about 30 minutes. I'm going to proceed. Okay. I'm going to proceed, folks, because you could always stop this. So we might as well have it in the one go. So let's go. Oh, right, go for this one. I'll get two open here, so that's why it's in. Doesn't matter. So, going to deal with things. Gradients of tangents. So gradients are derivatives. Tangents, we can think of them being lines that touch a curve. They're not always, tangents are not always lines. We can have a curve to the curve, two balls touching, two circles touching, okay? Right. And sometimes they use the phrase the rate of change. Rate of change means that we're going to be differentiating because we're looking at a gradient function. The rate of change, think of that as changing y over changing x, a gradient. So if you want a little picture there, I've given you one. I gave you one earlier. So we get some curvy thing, y equals f of x. Y is a function of x. So to get y, I need x processed through f. F is a function, the processor. And I'm picking a value here, x equals a. And when I pick that value of x equals a, I've just put a tangent line on that. And the gradient of the tangent line, that's the f dash part. Over here, the f dash, that's indicating I'm differentiating. And then when I insert a, I'll get the gradient m. The gradient m is the derivative. So I'll just end up with a number here. Okay, we're nearly there. So I've got a function f of x equals x cubed. I could write that as y equals x cubed, but I've got a number, I've got a specific number. X is 1.5, 1.5. If you want a picture here, I'll give you one. The curvy bit, that's x cubed, or a portion of it. I went along to the x-axis at 1.5, come up to the curve. When I touch the curve, I put on a tangent line, and the gradient of the tangent line is actually equal to the gradient or the derivative on the curve. That's what I'm looking for here. So all we need to do, we don't need a picture. This is what we need. Take the curve, that's 1x to the 3, ax to the n. Let's differentiate it. I'm using the f notation, so I'm going to use f dash. Okay, so that's 3x. The 3 comes down the front, subtract 1 for the power. Okay, I've now got a specific value for x, it's 1.5. So I'm using the function, so I'm using m to emphasize it's a gradient, and f dash is the gradient function or derivative at 1.5, so it's 3 times 1.5 squared. Put that in your calculator. Sometimes your calculators give you fractions back. Your calculator might give you 27 over 4, but you probably know how to deal with 27 over 4 with your calculator. If not, just do 27 divide by 4. And we should get a decimal answer. And that's it. That is a steepness at 1.5 on the curve x, y equals x cubed. That's what you found there. Okay, let's move on. I'm looking at sine x, we're looking at a value x equals pi over 3. Essentially, same type of question. You want a picture? There you go. There's sine x between 0 and 2 pi. Usually dealing in degrees, so it's 0 to 360, if you can remember that. But we're talking about pi over 3, that's like 180 over 3, 60 degrees. So pi over 3, that's a wee bit to the left. It's nearly at 0 there. So let's go up to the curve. Let's slap on a tangent line. I can see that's got a positive gradient there. So that just gives me an indication that I'm going to get a positive answer here. So this is what we really need to do. Take the original function y equals sine x, use the appropriate rule. Well, we've got sine ax plus b, but the number in front of x is 1, the b's value is 0, so sine just goes to cosine when I differentiate it. Okay, dy by dx or y dash, that's fine. Okay, but now we're going to take x equals pi over 3 and insert it into the derivative. Y dash equals cos x at pi over 3. Put it in. Make sure your calculator's in radian modes, because when calculus meets trigonometry, it can have problems. So it's best to be in radian mode. Nothing's natural in mathematics, but in terms of angles, they are as near to natural as we can get in maths in terms of angular measure. Okay, so cosine of pi divided by 3, that should give you a nice answer of a half. If you're getting something like 0.9 something or other, you're in degree mode. So speak to your lecturer, your best friend, whatever, and sort out. That's it done. Don't need a picture. Okay, let's move it up a stage. This time it's not y and x, it's q and t. Okay, so we'll get q, we'll get t. So q is like y, t is like x. Number in front of t is 2 pi. We can consider that to be the one number, just 2 pi. Let's differentiate it. So here's a question: determine the rate of change. Talking about differentiation here. Rate of change of q with respect to t at a specific value of 3 seconds. So here, let's just go and differentiate it. So the number in front of t comes out the front. The 2 pi multiplies a 10. Cos goes to negative sign, and the stuff in the bracket stays the same. We've got a specific value of t, that was 3 seconds. Let's put it inside. You would be able to type that into your calculator as it stands, just with the brackets. You don't need any multiplies. Your calculator would take care of it. If you want to sort out the contents of the larger bracket, see if you ignore the pi's, just type in 2 times 3 is 6 plus a quarter. Okay, that would give you 25 over 4 and stick pi next to it. That's how I got that. But your modern calculators would sort that out. So if you type that in the calculator, remember being on radian mode, what will happen here is it'll give you an answer. It'll probably give you a decimal answer. Probably give you negative 44.4. Right. So we don't know what units we're talking about here, because we're talking about changing charge with regards to time, but so we'll not talk about what that is. But if your calculator's in a different mode, it might give you an exact answer. Negative 10 times root 2 pi, that's fine. So it's whatever mode your calculator's in. I think it'll give you a decimal value there. Right, that's okay. So I'm going to continue. Just checking my time here, and I'm going to be back. So I'm just going to pause this, just go and get a drink of water, because I can hear my voice is getting a bit hoarse. But just hang in there, folks. I shall be back. I'll be back. Okay, you'd never even notice I've been away for 20 minutes. Not even that, eh? 6 o'clock in the morning. Here we go. Right, we're going to talk about these things called stationary points. And stationary points is a bad description. It doesn't matter. I'm going to give you a description. What exactly we're looking for here. So for us, stationary points on a function, that's your wee mathematical thing. Y equals whatever. It's where the derivative is exactly 0. And you know something, where the derivative is 0 is horizontal. The tangent line, the tangent curve is 0. So we have got a condition, our derivative dy by dx, y dash is equal to 0. That's very, very important. So, we have got types of stationary points where the derivative is equal to 0. Okay, so I'm just going to go through them. You might have seen them before. Please note in each of these, I'm going to have a horizontal line. It's some discrete point. Okay, so here it looks like a little hill. So it looks like we've got a maximum turning point there. And the opposite of that would be a minimum turning point. One that you've not seen, going from bottom left up to top right. What seems to happen in the middle is we get a sort of plateau. It flattens out in the middle. So the derivative is equal to 0 there. And the reflection of that, we call that a rising point of inflection. We're rising, going from bottom left to top right. Okay, its partner is a mirror image of that, and we call that a decreasing or a falling point of inflection. There's all four. The thing they all have in common is that at a specific point on them, the gradient function or the derivative is equal to 0. That's what we've got in common with them all. So you do not have to have intimate knowledge of graphs. What you need to know is to look for them. You need to get a derivative and make it equal to 0. That's what you're going to be doing here. So that's the build up. Okay. Let's just go for it here. And I'll just have a quick pause again before I come back. Okay. So in order to search for these stationary points, the derivative must be equal to 0. So let's go for a nice simple one here. As soon as you see the phrase stationary points, you know, oh sorry, because I'm telling you now, stationary points, you know they're talking about differentiation. Okay, please take that on board. See, when they talk about the nature, I don't like that description, but in mathematics and sciences and engineering, they use bizarre phrases. So the nature, it actually refers to what way is it kind of bending? Is it maximum, minimum, rising point of inflection, falling point of that? So that's what I mean by the nature. Which one of these are combinations? Is it going to be? So that's what they're talking about there. So we'll get this function y equals x squared, take away 5x plus 6. So let's just jump in here and go for it. So that's this looks okay. X squared, 1x to 2, so the 2 comes down the front, multiplies x, because we need a derivative. So I'm going to have 2x to the 1, just 2x. Number times x, I'm just going to be left with a number, -5. And the 6, it's a number on its own, it disappears. So that's my derivative. Okay. So now you've been practicing, right? And right, because you've had the lessons before, but in between this, you go back and practice this stuff. That's my derivative. Okay, I'm looking for stationary points. Where do I find them? Okay, not on IKEA, not on Argus, not on Amazon. I find stationary points where my derivative is equal to 0. dy by dx, because it's y as a function of x. Okay, so what I've got here, I've got a derivative and I've got a condition. Okay, there's my derivative, there's my condition. So we make them equal to each other. That's forcing the condition upon it. Okay, let's go for it and solve for x. 2x take away 5 equals 0, get rid of the 5, okay. 2x equals 5 divided by 2, 2.5 or 5 over 2, that's us. Done, easy. Right, okay. So what we're going to do here is use something called a nature table. It just tells you what's happening around about 2.5. How's it sloping towards it? How's it approaching it? Is it rising up towards it or coming down from the top towards it? And how's it leaving it? Right? Because we know at 2.5, it's horizontal, it's flat, it's a plateau. Okay, the gradient is 0 there. So we're going to use a nature table with this value of 2.5 in this case. This is called the critical value. We've only got one here, so this should be fine. So this nature table is comprised of 3 rows. So let's go for it. So the top row is the x's. Okay, so I'm going to put in some x numbers there. Second row is going to be the derivative numbers. And the last row is the nature. And that's just, I should have used a different colour there. This in the last row, that relates to the shape as it goes up, down, horizontal, whatever. So let's go for it. So I'm going to look at a number left and right of 2.5. It's up to you what numbers you pick. I'll pick whatever numbers. Right. A number to the left of 2.5, maybe 1, 1.5, that'd be fine. Number to the right of 2.5, could have 2.7, could have 5.92. Pick nice numbers, because you're going to be using them when you insert them into the derivative. So that's exactly what we're going to do, in a little bit. We're going to put them into derivative, but right away, underneath 2.5, the derivative is 0, because we forced the derivative to be 0, and it gave us 2.5. So that's done. Right, now we're going to look at 2 and 3 in the derivative. So our derivative was 2x take away 5, so I'm putting 2 in there. That's the number to the left. So 2 take away 2, 2 times 2 take away 5 is 4 take away 5 is negative 1. So we're highlighting it's negative here. Right. Let's deal with the next one. Look at the next one to the right of 2.5 is 3. Put 3 in. 2 times 3 take away 5. 6 take away 5 is positive 1. I want to emphasize put a positive there. Right? Because in the derivative column or row, it's the signs I'm interested in putting in here. Not the magnitude, the size of numbers, but the signs of the numbers. So negative and positive, that's what I'm interested in. So hopefully you can see what I'm doing there. I'm just putting in the signs here. Right. Signs have gone in. So we're going to now establish the nature of this. So this is the last row here. So the nature is just these really, think about these as being gradients of lines here. What does a negative gradient look like? A 0 gradient look like? And a positive gradient look like? So a negative gradient, kind of down from top left to bottom right. 0 gradient across, positive gradient, bottom left to top right. So that's kind of tracing out some kind of curve there. So what does that look like? Well, to me, that looks like a minimum turning point there. That's exactly what it is at the critical value of 2.5. That's us finished there. That's it done. Okay, let's go for another one. Exact same question, exact same scenario. We've just got a different function here. So we're going to go through the same process, differentiate it, set it equal to 0, solve for x, come up with a critical value, or maybe more than one critical value, and look left and right of them and see what's happening. Take that curve, use your knowledge, use your formula sheet, it's ax to the n, okay? So let's differentiate that. Hopefully you come up with that there. Okay. Again, condition for stationary points, because that's what we're looking for, is where the derivative is equal to 0. So make sure you write that down. There's a couple of things. If you are doing an assessment, well, they probably give you a mark for that. But the thing is, it lets you know what to do next. You're setting your derivative equal to 0. We've got a derivative, we've got a condition. Let's set it equal to 0. Right. So that looks like a quadratic because the highest power is 2. Any other power of x is not a fractional power, so it is a quadratic. So you can solve that. If you know how to solve quadratics, you could use quadratic formula. Whether you could factorize this, if you can, it's up to you. I'm just looking at the numbers in front of the x squared, the x, and the number on its own. I can spot that they're all divisible by 6, or multiples of 6. That's exactly what I'm going to do here. I'm going to divide them all by 6. So that doesn't matter. That's what I'm doing here. I'm dividing them all by 6. So what I've got here is, so again, I could use a quadratic formula either in this line or this line, but here I can factorize it. So two things to give me x squared, x times x, two things that multiply to give me 6, but add up to give me 5, and both must be negative. So what do you think there? You've already got notes on factorising, or you've done it in the past. So that's what I'm getting there. X take away 2 times x take away 3. The only way is that possible if the first bracket is equal to 0 or the contents of the second bracket are equal to 0. Now solve for x. On the left, x is equal to 2, and on the right, x is equal to 3. Here, we've now got two critical values. So I'm now going to use a nature table again here with these two critical values, but this time, because of two of them, I need to look to the left of 2, I need to look at the right of 3, and I need to look in between 2 and 3. Right, so I'm going to have to choose some other numbers. So there's my nature table. Again, it's got x numbers, my derivative values, or the signs, and then what is happening in the curve. How's it bending? What's the shape? Right, so it's up to you. What numbers do you want to pick? So between 2 and 3, could pick 2.1 or 2.9, could do that. A number bigger than 3 could pick 15 or 17. Number below 2 could pick negative 17 or 1.9. Pick sensible numbers, because it's you it's going to use them. So did you choose these numbers, the ones that we're going to use, and we're going to put them in the derivative? That's what I've picked. 1, 2.5, and 4. They seem to work for me. I'm going to put them now in the derivative. What was the derivative? I'm doing this from memory. 6x squared take away 30x plus 36, I think. Right, but underneath, automatically, underneath the critical values here, underneath 2, underneath 3, we know the derivative is equal to 0 because before start to be equal to 0, that's how we got the 2 and the 3. Right, okay, get the derivative. There, that was our derivative. Let's start putting in 1, 2.5, and 4 into our derivative. Okay, put them in, but it's a sign of the number because you might have picked different numbers from me. You might not have picked 1, you might have picked 0.5 or whatever, but it doesn't matter. The sign of the number will be the same as I have got. So the sign, my number is going to be positive 12 there. Right, so it's that positive. That's going to go up there once I've got my other ones. That's the way. If you want to put it in there right away, that's fine. It's up to you. Right, next one, 2.5. Okay, just you type it in, see what your calculator gives you. It's a sign that's important. Is it positive or negative? I'm getting negative 1.5. That's fine. Finally, the third one, number greater than 3, so I'm using 4. Put it in, and I'm getting a number. Is it positive or negative? It's positive and it's 12. Right, that's fine. So, for little equations there, we don't need them anymore. Okay, don't need them. It's these answers here that I need, the signs of the answers. That's what I'm interested in. These signs. So, take the signs and insert them, okay, into the derivative rule, dy by dx. Okay, they're getting there. That's fine. So now, remember, these signs, think of them as relating to the slope of lines. Okay, so for a tangent, so a nature means slope. Okay, so going from the left, so positive here. What am I going to get for a positive? Rising up. Okay, that's fine. 0, you know 0 is going to be going across. Negative, you know that's going to be going down a way. Again, a 0 here, you know it's going to be going across. And finally, a positive, you know that's going to be going up the way. So these sort of trace out what we're interested in. So what we're interested here is what is happening at the critical values only, so left and right. So just to emphasize, so here at 2, what's happening to, I don't think it's playing today. It's disappearing. Right, what's happening to, yeah. So at 2, at x equals 2, it looks as if it rises to a maximum value. So it looks like that's what we're finding here. So at 2, it's going to be a maximum. And see at 3, you just look at either side. And then we're going to do likewise. What's happening round about x equals 3? Again, so it looks as if it's bottoming out there. So that looks like a minimum there. And we actually just need to state that. So the critical value at x equals 2, what's happening either side? Well, it looks as if it's maximising at x equals 2. And again, at x equals 3, it looks like as if it's bottoming out there. So as long as you put that there, then that is us done. Right, okay. So in the first one, we only had one critical value. This one with 2 critical values. Oh, let's see what we're going to have next. Okay, so what we're going to have next okay, right, we're upping it here. This is x to the 4. What does this tell us? Well, it tells you about critical values. You won't get 4. The maximum you'll get is 1 less than that. So it could be 3, could be 2, could be 1, and actually, it could be 0. Right? But the maximum you get is actually 1 less than the highest power. So maximum points in maximum stationary points is going to be 3 here. Right? That gives you a wee clue. So if you end up with 5, you've done something wrong. Right, so same process as before. Let's differentiate it. So again, 4 times x to the power 3, because we're subtracting 1 to the power. 2 times the negative 8 is negative 16. Subtract 1 from the 2 is 1. So that's our derivative there. As before, state the condition where stationary points exist, where the derivative is equal to 0. Now force that condition. Let's solve it. Okay, so here it looks as if we're going to have to factorize here. So 4, 16, looking at these two numbers, they're divisible by 4, so 4 is a factor. We've got an x cubed, we've got a single x. So it looks like the single x, x to the power 1, that's what I remember single x. So it looks like 4x is a common factor. Let's bring it out and divide the contents, the original contents by 4x. We should end up with that. Okay, so we'll factorize it. I could factorize it further, right? But I won't. I'm just going to make 4x equal to 0 and make the contents of the bracket equal to 0. Okay, so 4x is equal to 0. 4 times what gives you 0? Well, just take x equals 0 divided by 4 to get 0. X squared taken by 4 equals 0. Several ways you can solve this. Isolate x squared if you want to do that. Take the square root of 4. Here, we don't know what we're dealing with. We've got no context. So when you're square rooting a positive value, there's always two possible answers, a plus or a minus, positive or negative. Square root of 4. We've spoken about this in class. Okay, so we've got two answers there. So in total, we get 3 answers or 3 critical values. Right. So, and I keep on saying again, rewind this if you're not quite getting this. But the thing is, if you're not getting this, there's other stuff you've not got from before. So go back and look at that. Factorising, stuff like that. Right, so the critical values are definitely negative 2, 0, and positive 2. I'll put them in order, going from left to right, smallest to biggest. Let's set up a nature table again here. Okay, it's getting longer, but we've still got 3 rows. Right, but notice here, I'm looking at a number to the left of negative 2, between negative 2 and 0, between 0 and 2, and a number greater than 2. You pick whatever numbers you want, because the signs that will appear in here, positive zeros and negatives, whatever they are, will be the same, and that will determine which way this thing is sloping. Okay, right, so we're going to pick numbers. You might have guessed, or if you've been in the class and seen this wee part of the lesson, that's the numbers I picked, as long as they fit in, right, with the criteria, like between 0 and 2, between 0 and negative 2, bigger than 2, less than negative 2. As long as they fit in, right away, under the critical values, you know the derivative is 0 because you made the derivative 0 and it gave you negative 2, 0 and 2. Right, let's use the derivative. Okay, it was 4x cubed take away 16x, so I'm just putting in the numbers here. I'm just going from left to right with the four of them, put them in, just get the answers, and it's a sign of the answer you're interested in. So, won't waste your time. As I keep saying, you can freeze that if you don't believe me. There's the first one at -3, second one at -1, get an answer. It's just +12. Make sure you have the plus sign, which is a positive, whatever. Next one at +1, get an answer. That's fine. And finally, at +3, put it in, get an answer. That's fine. So, done our calculations. It's these parts at the end. Negative, positive, negative, positive. That's what I'm interested in. Okay. These signs here, these signs are going to go up into their appropriate slots here. That's what's going to happen next. Put them in the correct slots, the signs and not the magnitude, the size of the number. Put them in, and then that will dictate what's happening down here. Okay, so let's start. So something with a negative gradient. Okay, it's going down. Zero gradient, going across. Positive gradient, then up. Zero gradient, going across. Negative, and down. Zero, going across. Positive, going up. So this is tracing out what is happening. So round about zero, and actually zero is an x value, right? So it's what is happening at the x value of zero. Looks as if it's maximizing there. And finally at 2, looks as if it's minimizing, and at -2, looks as if it's minimizing there. So I'm just going to state that there for each of them. Okay. Um, what happens if you don't like the second derivative test? Oh, sorry. You don't like the nature table. We can use the second derivative test. So the second derivative, I'm going to use the notation y double dash here. So y dash is the first derivative, y double dash is the second derivative. So if you have a critical value and you put it in to y double dash and you get a positive answer, it tells you got a minimum turning point. We'll talk about this later on. But on the other hand, if you put in the critical value to y double dash, the second derivative, and you get a negative value that's less than 0, there's a maximum turning point. Like I said, I'll give you a method later for this. Right. Oh, but there's a number missing here. What answer have I not accounted for? So y double dash is either positive, it's negative. So what's the number we haven't looked at? Well, 0. So if the second derivative y double dash is 0, is it a minimum? Is it a maximum? Is it one of those other strange things we've not talked about, points of inflection? No, it doesn't give us any information. We need to go back to a nature table. Okay, but what I'm going to do here is I'm actually going to look at sorry, just a wee recap. Right, so we're going to look at this, but we've actually, this is the one we've just looked at, but we're going to look at it in a different way. We're not going to use a nature table. So we're going to use this second derivative test. There's the first derivative. We had that before, but here's the second derivative. So 3 times 4 is 12. 3 take away 1 is 2, so we're going to have 12x squared. Take away 16. It's just going to be take away 16 because it's a number times x. That's the second derivative. That's what we're going to be using here. We already know the critical values because we worked that out in the previous questions. Negative 2, 0, and 2. So what we're going to do here is we're going to put them in. So put in negative 2 first, and I'm just showing you the answers. Positive 32. Right, so how do we know? Because the answer's not 0, it's either a maximum or a minimum. Let's think about your your demeanour or your disposition. That just means how you're feeling. So if you're positive, are you feeling happy or sad? Well, I'm feeling happy. Okay, so happy. Oh, look at that curve. Look at that curve there. How's that curving? Does that reflect a min or a max? It's a minimum. That's how I remember. Let's put in now 0 into 12x squared take away 16. And when I put that in, I get a negative answer. So negative in terms of how you're feeling, your disposition. Negative, oh, you're not happy, you're sad. But look at the way it's tracing out there. Does that look a max or a min? It's a max. Right. Fine. And finally, let's put in 2. So 12 times 2 squared take away 16. So that's 12 times 4, 48. Take away 16. That gives a positive 32. Again, positive. How are you feeling? You're feeling happy, which means it's a minimum. Okay. So that's how the second derivative test works. It lets you know. Okay. Some people think this is a lot quicker, but it doesn't always work. Okay. And I'll just show you why it doesn't always work. Here's a function I've not looked at here. Let's just go through it. Need to go through it from scratch. First derivative. Okay. You should know how to get it. I don't need to explain it. Second derivative. Okay. Right, I need to go back to the first derivative now to find my critical values. I need to make my first derivative equal to 0. Done. Okay. Divide both sides by negative 96. So if x to the 5 equals to 0, so if x to the power of anything apart from 0 is equal to 0, that means x is 0. Okay. Take that on board. Laws of indices. Stuff you've done in the past. Please remember it, folks. Right. I've only got one critical value. So I'm going to put this into my second derivative and it's going to let me know, do I have a max or a min? Put it in. At x equals 0, put it in my second derivative. 0 to the power 4 is 0. Anything times 0 is 0. So that there, what does that tell you? The second derivative test giving me 0. It tells me nothing. So that's a total failure of the second derivative test. What does that mean? Well, it means we have to go back and use the nature table. So this is, so I've actually condensed quite a lot into this little video. But the thing is, it's for your benefit, because I'm sitting in my house doing this, right, at times when I shouldn't be doing this, and I'll get no thanks. I know that. Right. Anyway, I am going to close it there. So now a quarter. Right, that's okay. Right, Tommy, I'll close it. Right, folk, you have a look at your revision sheets, go through it. There'll be other stuff. So this was the bare minimum, right? But it's additional. It's more than a lot of other folk will give you. Right. Bye for now.